Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read, recorded, and produced by JohnLothe. Chapter 13. Temperature. Hot and cold. Heat has been mentioned several times in the book, notably toward the end of Chapter 7, in connection with the conservation of energy. I have not stopped, however, to consider it in detail, since to do so with proper understanding required first a consideration of the properties of fluids, and, in particular, of gases. Enough of these properties have now been described to make it advisable to turn again to the subject of heat. Heat is most familiar to us as a subjective sensation. We feel something to be hot or cold, and we know what we mean when we say that one object is hotter than another. The degree of hotness or coldness of an object is called its temperature. Temperature is of importance to physicists because a great many of the properties of matter with which he deals vary with temperature. In the previous chapter, for instance, I mentioned that the velocity of sound varied with temperature. See page 164. Again, the volume of a given mass of water increases as it is heated to near the boiling point, and so the density decreases. Hot water possesses weaker cohesive forces than does cold water, so the viscosity and surface tension decrease as temperature goes up. Even such seeming unchangeables as the length of an iron rod change with temperature. It follows, then, that if a physicist is to make proper generalizations concerning the universe, he must know just how the properties of matter change with temperature, and to do that, he must be able to measure the temperature accurately. Our subjective feelings are insufficiently fine under the best conditions, and are grossly inaccurate at times. Therefore, they will not do for the purpose. Thus, a polished metal surface exposed to the temperature of freezing water will feel much colder to the touch than a polished wooden surface exposed to the same conditions, for reasons to be discussed on page 225, even though both are at the same temperature. A well-known experiment produces an even greater paradox. If you place one hand in ice water and one in hot water and leave them there for a few moments, and then place both hands in the same container of lukewarm water, you will simultaneously feel the lukewarm water to be warm with your cold hand and cold with your hot hand. Some objective means of measuring temperature is therefore needed. The logical method is to find some property that changes in an apparently uniform manner with temperature, and then associate fixed changes in temperature with fixed changes in that property. Physicists make use of a number of different temperature-dependent properties for the purpose, but the most commonly used property for the temperature range met with in ordinary life is that of volume change. The volume of a given mass of matter generally increases with rising temperature and decreases with falling temperature. I say generally because there are occasional exceptions to this. The change in volume with temperature is, in the case of liquids and solids, quite small and, in fact, unnoticeable to the eye. Thus, a steel rod, a meter long, will, if brought from the temperature of melting ice to that of boiling water, expand in length by 1 millimeter. That is, 1 part in 1,000. So it is the volume that is expanding. The other dimensions will also increase by 1 part in 1,000, and if the steel rod has a circular cross-section 1 centimeter in radius, that radius will increase by 1/100th of a millimeter. Such changes, while small, are by no means unimportant. Long metal girders, such as those used in bridges, or long rails, such as those used in railroad tracks, will expand and buckle in the hot summer sun if fixed at both ends. To avoid that, spaces are left between adjoining units, so that there will be room to expand. Again, even a trifling change in the length of a clock's pendulum will alter its period slightly, for that period depends upon its length. See page 112. The error in time measurement, which depends upon that period, is cumulative, and would make it necessary to adjust the clock periodically in summer. although it might run perfectly at cooler temperatures. Not all substances expand by the same relative amounts when exposed to a given temperature change. An alloy of iron and nickel in 5:3 ratio will, for instance, only expand to 1/10 the extent that iron or steel will. For this reason, it is a useful alloy out of which to construct measuring tapes, rods of standard length, and so on. Because its length is more nearly invariable than that of most metals, the trade name for the alloy is invar. Glass expands with temperature almost to the same extent that steel will. If a glass vessel is exposed to a drastic temperature change, one portion of it may expand or contract, while another portion, to which the temperature change has not yet penetrated, does not. The expansion or contraction may not be large in an absolute sense, but it is enough to set up internal strains, which the cohesive forces of glass are not sufficient to withstand. So, the glass cracks. One way out of this dilemma is to use relatively thin glass, so that if one portion is heated or cooled, the temperature change will penetrate to other portions quickly. Another and better way is to make use of a boron coating variety of glass, usually known by the trade name of Pyrex, which will change in volume with a given temperature only by 1/3 the amount that ordinary glass will. It is therefore far more resistant to cracking under temperature change because smaller strains are set up. Its thickness and mechanical strength need not therefore be sacrificed to temperature stability. Quartz, with a still smaller tendency to change volume with temperature, less even than that of invar, is still better for the purpose. A quartz vessel can be heated to red heat and plunged into ice water, and be undamaged by the ordeal. However startling the effects of trifling changes in volume, those changes remain trifling in actual size. Unless they can somehow be magnified, they would be difficult to use as a measure of temperature. Fortunately, there are simple methods of magnifying small volume changes. One method is to weld strips of two different metals together, say a strip of brass with one of iron. For a given change of temperature, a brass strip will change in volume, and therefore in length, to nearly twice the extent that an iron strip of the same size will. If the two strips of metal were not welded together, the brass would expand under the influence of increasing temperature and slide against the iron, becoming a trifle the longer of the two, although they had been equal in length to start with. If the temperature is reduced below the starting point, matters are reversed. Now the brass contracts more than the iron does, sliding against the iron and ending a trifle the shorter of the two. However, the two strips of metal are welded together, and the brass cannot slide against the iron. What happens then is that the welded strips, a bimetallic strip or a compound bar, bend in the direction of the iron if it is heated. The brass would then lie along the outer rim of the curve and the iron along the inner. Since the outer rim is longer than the inner, this allows the brass to be longer than the iron while remaining welded throughout. As the temperature falls again, the curve straightens and becomes entirely straight when the temperature returns to its original value. If the temperature falls lower still, the bimetallic strip bends in the direction of the brass, which now lies on the inner rim while the iron lies on the outer rim. If such a bimetallic strip is fixed at one end, the other end sways back and forth as temperature changes. The outer rim of the curved strip is very little longer than the inner, and the difference in length increases but slowly with the degree of bending. For that reason, even small changes in temperature, producing very small differences in length between the iron and brass, nevertheless produce a considerable amount of bending. A device of this sort can be used as a thermostat. As the temperature in a house falls, the bimetallic strip begins to curve to the left, let us say, and at a certain temperature the bending is sufficient for it to close an electrical contact that turns on the furnace. As the house heats up, the bimetallic strip bends back and quickly breaks the contact, thereby turning the furnace off. By altering the position of the electrical contact, easily done by hand, we can arrange to have the bimetallic strip turn the furnace on at any temperature we please. Then, too, the exact position of the free end of such a bimetallic strip can be used as a measure of the temperature. If a pen is attached and a circle of paper is allowed to revolve under it at a fixed speed, the device will automatically make a continuous recording of its position. The temperature can be deduced from the position of the wavering line. Again, pendulums can be designed in which the rod is not a single piece of metal, but several strips of two different metals, say steel and zinc. These can be joined by horizontal bars in such a way that the temperature change in the zinc tends to lengthen the pendulum, while the temperature change in the iron tends to shorten it. The combined actions tend to leave the pendulum unaltered in length as temperature changes. This is a compensation pendulum. Temperature scales. A much more common method of magnifying volume change for the purpose of measuring temperature is to make use of liquids rather than solids. Imagine an evacuated spherical container with a long, narrow tube of constant width extending upward. The container holds enough liquid to fill the sphere completely, but the neck remains empty and includes only vacuum. If the liquid is warmed, its volume will increase and there will be no place for the liquid to expand into but the neck. The volume of the water rising into the cylindrical neck can be expressed by the usual formula for the volume of a cylinder. V equals pi times r squared times h, where r is the radius of the cylindrical neck and h is the height to which the water rises. For a given volume, the smaller the value of the radius of the neck, the greater the height to which the liquid must rise. It follows that even though the additional volume of liquid due to expansion with temperature is very small, the change in height can be made quite sizable if only the radius of the tube is made small enough. There is no difficulty in using changes in the height to measure changes in temperature. A device making use of a sizable reservoir of fluid and a narrow tube into which that fluid can expand is the most common form of thermometer, from Greek words meaning heat measure. Such thermometers were first devised in the 17th century, and a variety of fluids were used. Water, naturally, was one of the first. Unfortunately, water does not expand uniformly with temperature. In fact, it reaches a point of maximum density and minimum volume at a temperature somewhat above its freezing point. If the temperature is dropped further, water actually expands as the temperature is lowered until it freezes, and in that process expands still further, for ice is less dense than water by nearly 10%. Furthermore, water remains liquid over a comparatively small temperature range and is useless for temperatures below its freezing point or above its boiling point. Alcohol, also used in thermometers, stays liquid at temperatures far below that at which water freezes. However, it boils at a temperature even lower than that at which water boils. Furthermore, both water and alcohol wet glass. As the height of liquid sinks with the falling temperature, some remains behind, clings to the glass, and then slowly trickles down. The level of liquid may then be observed to rise slowly, and it would be difficult to decide whether this was because temperature was going up or liquid was trickling down. The first to make use of mercury as a thermometric fluid was a German physicist named Gabriel Daniel Fahrenheit, 1686 to 1736, and he did this in 1714. Mercury's freezing point is considerably below that of water, and its boiling point is considerably higher. In addition, it expands quite smoothly with temperature changes. One way of judging this is by noting that temperature changes, as measured by the change in volume of mercury, agree closely with temperature changes as measured by changes in a variety of other properties of matter. It is more reasonable to assume that all these changes are regular than that they all happen to be irregular in just the same way. Finally, mercury does not wet glass, and the height of the mercury column would not be affected by delayed trickling. Once the course of temperature change is made easily visible by the rise and fall of the mercury thread in the narrow tube of the thermometer, it is next necessary to associate some definite numerical values with fixed positions. At atmospheric pressure, for instance, ice melts at a particular temperature, and there seems every reason to believe that this temperature is the same in all places and at all times. At least, there is no reason to believe the contrary. Similarly, water always boils at a particular temperature at atmospheric pressure in all places and at all times. If a thermometer is placed in melting ice, the level to which the mercury thread rises can be marked. If it is placed in boiling water, a new level is marked. All men would have marks on their own thermometers that were comparable. All thermometers would match and speak the same language. Once two such marks were set, the distance between could be divided into equal steps, or degrees. Fahrenheit's method of setting his fixed point unfortunately did not involve the freezing point and boiling point of water directly. For his 0 point, he used a mixture of ice and salt that produced the lowest freezing point he could get. And for another point, he tried to use the temperature of the human body. He ended by associating the freezing point of pure water with the number 32, and the boiling point of water with 212. These figures are separated by 180 degrees, you see. This is the Fahrenheit scale, and measurements upon it are given in degrees Fahrenheit, abbreviated as degrees F. Thus, the freezing point of water is 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit. Body temperature is set at 98.6 degrees Fahrenheit, and something like 70 degrees Fahrenheit is considered a comfortable room temperature. Temperatures below the 0 degrees Fahrenheit mark can be said to be so many degrees below zero, or a minus sign can be used. Thus, alcohol freezes at 179 degrees below 0 Fahrenheit, or at negative 179 degrees F. In 1742, the Swedish astronomer Anders Celsius, 1701 to 1744, made use of a different scale, one in which the freezing point of water was associated with 0 and the boiling point with 100. These points, therefore, being separated by 100 degrees. This scale is called the centigrade scale, from Latin words meaning 100 degrees. But in the 1950s, it was decided to honor the inventor by calling it the Celsius scale, whether one speaks of degrees centigrade or degrees Celsius. However, the abbreviation is degrees C. On the Celsius scale, the melting point of ice, or the freezing point of water, is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. The Celsius scale commends itself to scientists because the 0 to 100 stretch fits in with the decimal nature of the metric system, and because the stretch of temperature over which water remains liquid is a particularly interesting one, especially to chemists. It is the Celsius scale that is used universally by scientists. The Fahrenheit scale, however, is used in ordinary affairs in the United States and Great Britain, and it has at least this advantage. The 0 to 100 stretch in the Fahrenheit scale covers the usual range of temperature in the world. Meteorologists using the Celsius scale must frequently descend to negative numbers. Those using the Fahrenheit scale need do so but rarely. Since both scales are used in the United States and Great Britain, it is useful to be able to convert one to the other. Let us begin by noting that in the range between the freezing point and the boiling point of water, there are 180 Fahrenheit degrees and 100 Celsius degrees. The Celsius degree is obviously the larger of the two, and is equal to 180 divided by 100, or 9 divided by 5 Fahrenheit degrees. Conversely, a Fahrenheit degree is equal to 100 divided by 180, or 5 divided by 9 Celsius degrees. That would be enough if the two scales had their 0 point in common, but they don't. If the Celsius reading is multiplied by 9 divided by 5, the result is the number of Fahrenheit degrees, not above 0 degrees Fahrenheit, but above 32 degrees Fahrenheit. For 32 degrees Fahrenheit is the equivalent of 0 degrees Celsius. For that reason, 32 degrees must be added to the result. In other words, F equals 9 divided by 5 times C plus 32. Equation 13-1. To obtain the reading on the Celsius scale, when the Fahrenheit temperature is given, it is only necessary to solve equation 13-1 for C, and the answer is C equals 5 divided by 9 times F minus 32. Equation 13-2. Expansion. Once temperature can be measured with precision, it becomes possible to express temperature-dependent changes accurately. We can decide how much change there is per degree Celsius, a phrase that can be abbreviated as per degrees C or /degrees C. For instance, we can measure the changing length of a rod and determine the increase of length brought about by a definite temperature change. We can then calculate what the relative increase in length is for a rod that has undergone a temperature rise of 1 degrees Celsius. This increase is the coefficient of linear expansion. The size of the coefficient of linear expansion varies from substance to substance, but for solids, it is always quite small. For steel, for instance, it is 0.00001 per degrees Celsius, or, expressed in exponential form, 1 times 10 to the negative 5th power per degrees Celsius. This means that a 1 meter rod will expand by 0.00001 meters when temperature goes up 1 degrees Celsius. A 1 kilometer rod will expand by 0.00001 kilometers. A 1 centimeter rod will expand by 0.00001 centimeters, and so on. Some other coefficients of linear expansion are 1.9 times 10 to the negative 5th power per degrees Celsius for brass, 2.6 times 10 to the negative 5th power per degrees Celsius for aluminum, and only 0.04 times 10 to the negative 5th power per degrees Celsius for quartz. Suppose we represent the coefficient of linear expansion by the Greek letter alpha. If we start with a rod exactly 1 meter long at a particular temperature and raise that temperature by 1 degrees Celsius, then the length increases by alpha meters, and the total length is 1 plus alpha meters. If we raise the temperature by 2 degrees Celsius, then expansion is twice as great. So, the total length now becomes 1 plus 2 times alpha, while for a temperature rise of 3 degrees Celsius, it is 1 plus 3 times alpha. In short, the value of alpha is multiplied by the number of degrees by which the temperature is changed. It is customary in physics and in mathematics to signify a change in a value by the capital form of the Greek letter delta. If we let temperature be symbolized as T, then a temperature change is written delta T and is usually read delta T. In other words, we can consider the length of a 1 meter rod after a certain rise in temperature to be 1 plus alpha times delta T. Naturally, if temperature is allowed to fall instead of rise, delta T is negative, and so is alpha times delta T. The expression 1 plus alpha times delta T is then smaller than 1, which is reasonable, since with falling temperature the rod contracts. Suppose, now, that we started with a 2 meter rod. We can consider it as consisting of 2 1 meter rods fused together. Each 1 meter half has a total length of 1 plus alpha times delta T, after the temperature has changed, and the total length is therefore 2 times 1 plus alpha times delta t. This can now be reasoned similarly for... Similarly, there it is again. This can now be reasoned similarly... No, I said that right. This can now be reasoned similarly for any length. In fact, if we call the length of a rod L, then the new length after a change in temperature is L times 1 plus alpha times delta t. Or, multiplying this out, L plus L times alpha times delta t. We can next ask ourselves what the change in length is as a result of the change in temperature. The change in length, which we can naturally symbolize as delta times L, would be the length after the temperature change minus the original length. This would be L plus L times alpha times delta t minus L. So we can conclude delta times L equals L times alpha times delta t. Equation 13-3. A substance expanding with rise in temperature expands in all directions and not in length only, and the change in volume is often more important than the change in length. In liquids and gases, particularly, it is the expansion in volume that is measured. In solids, however, especially when in the shape of long rods, it is far simpler to measure the linear expansion and calculate the volume expansion from that. We can begin by assuming that the coefficient of linear expansion for a given substance has the same value for width and height as for length. Suppose we start with a cubic meter of a substance. Its length, after a 1 degrees Celsius rise in temperature, becomes 1 plus alpha meters. Its width, however, also expands to 1 plus alpha meters, and its height too. Its volume, which began as 1 to the third power cubic meters, 1 to the third power equals 1, of course, is now 1 plus alpha to the third power cubic meters. The change in volume with a 1 degrees Celsius rise in temperature is 1 plus alpha to the third power minus 1 to the third power, or 1 plus alpha to the third power minus 1. And that is the coefficient of cubical expansion. The quantity 1 plus alpha to the third power can be expanded by ordinary algebra to 1 plus 3 alpha plus 3 alpha to the second power plus alpha to the third power. We subtract 1 from this and find that the coefficient of cubical expansion is 3 alpha plus 3 alpha to the second power plus alpha to the third power, where alpha is very small, as it is in the case of solids and liquids. Alpha to the second power and alpha to the third power are much smaller still, and can be ignored as not contributing a significant quantity to the expression. If we throw out the square and cube, then we can say with quite sufficient accuracy that the coefficient of cubical expansion is 3 alpha minus 3 times the coefficient of linear expansion. Thus, if the coefficient of linear expansion is 1 times 10 to the negative 5th power per degrees Celsius for steel, then we can say that its coefficient of cubical expansion is 3 times 10 to the negative 5th power per degrees Celsius. The coefficient of cubical expansion is roughly 10 times as high for liquids as for solids, and considerably higher still for gases. It is, indeed, for gases that the coefficient of cubical expansion has proved to have the greatest theoretical significance. Galileo himself realized that gases expand with rising temperature and contract with falling temperature. He even tried to construct a thermometer based on this fact. Taking a warmed glass bulb with an upward stalk open at the top, he upended it in a trough of water. As the glass bulb cooled, the gas within it concentrated and water was drawn partway up the stalk. Later, if the temperature went up, the gas within the bulb expanded, pushing the water level in the stalk downward. If the temperature went down, the water level rose. Unfortunately for Galileo, The water level in the stalk was also affected by changes in air pressure, so the thermometer was not an accurate one. However, the principle of change in gas volume with change in temperature was established. Since this is so, then a volume of gas trapped under a column of mercury, as in Boyle's experiments, would expand if heated or contracted if cooled. This means that if one were studying the manner in which the volume of gas changed with changes in pressure, one would have to be sure to keep the gas at constant temperature. Otherwise, changes in volume would take place for which pressure was not responsible. Boyle himself, in formulating what we call Boyle's law, did not, apparently, take note of this fact. In 1676, however, a decade and a half after Boyle's experiments, a French physicist, Edmé Mariotte, 1620 to 1684, discovered Boyle's law independently, and he did draw attention to the importance of constant temperature. For this reason, on the European continent, the relationship of pressure and volume is often called Mariotte's law, rather than Boyle's law, and with some justice. The first attempt to study the expansion of gases with temperature change quantitatively was in 1699. The first attempt to study the expansion of gases with temperature change quantitatively was in 1699. The French physicist Guillaume Amontons, 1663 to 1705, showed that if the gas were pinned in and prevented from expanding as the temperature rose, the pressure increased instead, and that the pressure increased by a fixed amount for a given temperature rise, regardless of the mass of gas involved. Amontons, however, could work only with air, for in his time air was the only gas readily available. All through the 18th century, however, a number of gases were produced, distinguished among and studied. In 1802, the French chemist Joseph-Louis Gay-Lussac, 1778 to 1850, not only determined the coefficient of cubical expansion for air, but showed that the various common gases, such as oxygen, nitrogen, and hydrogen, all had just about the same coefficient of cubical expansion. This is quite astonishing, since the coefficient of cubical expansion varies quite a bit from one solid to another and from one liquid to another. Thus, the coefficient of cubical expansion is 77 times as great for aluminum as for quartz, and 6 times as great for methyl alcohol as for mercury. The coefficient of cubical expansion for gases at 0 degrees Celsius turns out to be 0.00366, or about 300 times the coefficient of cubical expansion for the average solid. We can adapt equation 13-3 for the expansion of gases. We will substitute volume, capital V, for length, and the coefficient of cubical expansion, 0.00366, or 1 divided by 273, for the coefficient of linear expansion. If we do this, then for the change in volume of gases, delta times capital V, with change in temperature from 0 degrees Celsius, delta times temperature, we can write delta times capital V equals 0.00366 times capital V times delta times temperature equals capital V times delta times temperature divided by 273. Equation 13-4. This is one way of expressing Gay-Lussac's law. As it happens, the French physicist Jacques-Alexandre César Charles, 1746 to 1823, claimed to have reached Gay-Lussac's conclusions as early as 1787. He did not publish them either then or later, and ordinarily, a discovery does not count unless it is published. Nevertheless, the relationship is frequently called Charles' law because of this. Absolute temperature. The fact that objects expand and contract with temperature change raises an interesting point. It is easy to see that an object can expand indefinitely as temperature goes up, but can an object contract indefinitely as temperature goes down? If it continues to contract at a steady rate, will it not eventually contract to zero volume? What then? The paradox is most acute in the case of gases, which contract more rapidly with falling temperature than do liquids or solids. The volume of a gas after a certain change in temperature from 0 degrees Celsius is the original volume at 0 degrees Celsius plus the change in volume, V plus delta times V. Suppose, then, that the temperature were to drop 273 degrees below 0 degrees Celsius. In that case, delta times temperature would be negative 273. From equation 13-4, we would see that delta times capital V, in that case, would be equal to capital V times negative 273 divided by 273, or to negative capital V. The new volume, capital V plus delta times V, would become capital V minus capital V, or 0. A strict application of Gay-Lussac's law would indicate that gases would reach zero volume and vanish at negative 273 degrees Celsius. Physicists did not panic at this possibility. It seemed quite likely that before negative 273 degrees Celsius was reached, all gases would be converted to liquid form, and for liquids, the coefficient of cubical expansion would then be much smaller. This turned out to be true. Even if this were not so, it seemed quite likely that Gay-Lussac's law might not apply strictly at very low temperatures, and that the coefficient of cubical expansion might gradually decrease as temperature dropped. So, although volume continued to shrink, it would do so at a slower and slower rate, and never reach zero. Nevertheless, the temperature, negative 273 degrees Celsius, was not forgotten. In 1848, William Thomas, later raised to the rank of Baron and the title of Lord Kelvin, pointed out the convenience of supposing that negative 273 degrees Celsius might represent the lowest possible temperature, an absolute zero. If we let negative 273 degrees Celsius be zero and count upward from that by Celsius degrees, we would have an absolute scale of temperature. Readings on this scale would constitute an absolute temperature, and the degrees given in such a reading could be indicated as degrees capital A for absolute, or, more often, as degrees capital K for Kelvin. To change a Celsius temperature to 1 on the absolute scale, it is therefore only necessary to add 273. Since water freezes at 0 degrees Celsius, it does so at 273 degrees Kelvin. Since it boils at 100 degrees Celsius, it does so at 373 degrees Kelvin. To prevent confusion, it is customary to represent temperature readings on the Celsius scale by the symbol T, and temperature readings on the Kelvin scale by the symbol capital T. We can write the relationship of the Kelvin scale to the Celsius scale as follows. Therefore, capital T equals T plus 273, or Kelvin temperature equals Celsius temperature plus 273. Equation 13-5. Footnotes. It is important to remember that many scientific generalizations hold true only over limited ranges of pressure, temperature, and other such environmental factors. This does not affect the usefulness of the generalization within the proper range, but one must not expect them to be useful outside that range. The actual value, according to the best modern determinations, is negative 273.16 degrees Celsius. Confusion cannot be done away with altogether. Thus, T stands not only for Celsius temperature, but also, very commonly, for time. Every letter of the Latin and Greek alphabet, and some from Hebrew, Sanskrit, and others, in small form, capital form, italics, boldface, and Gothic script, has been used. And even so, there are numerous duplications of symbols. For that reason, in presenting any equation, it is always advisable to state the significance of each symbol, and never to take it for granted that the meaning of any symbol is self-evident. The convenience of the absolute scale rests on the fact that certain physical relationships can be expressed more simply by using capital T rather than lowercase t. Thus, suppose we try to express the manner in which the volume of a quantity of gas varies with temperature. We can start at a temperature, let's say T1, with a gas at volume capital V1, and when the temperature has changed to T2, we will find that the gas volume has changed to capital V2. The volume will be the original volume plus the volume change. So, capital V2 equals capital V1 plus delta times capital V. Using equation 13-4, we see that delta times capital V equals capital V1 times delta times T divided by 273. However, the change in temperature, delta times T, is the difference between the final temperature and the original temperature. T2 minus T1. The unit of cubical expansion for gases is determined for a starting temperature of 0 degrees Celsius, so T2 minus T1 becomes T2 minus 0, or simply T2. We will therefore substitute T2 for the delta times T in equation 13-4. Then in writing, capital V2 equals capital V1 plus delta times capital V, we will have capital V2 equals capital V1 plus capital V2 times T2 divided by 273 equals capital V1 times 1 plus T2 divided by 273. Equation 13-6. This is easily converted to capital V2 divided by capital V1 equals 273 plus T2 divided by 273. Equation 13-7. Let's now consider what the significance of the number 273 might be. It enters this equation because 1 divided by 273 is the coefficient of cubical expansion for a gas at 0 degrees Celsius. Remember, however, that the unit of the coefficient of cubical expansion is per degrees Celsius, or /degrees Celsius. The number 273 is the reciprocal of that coefficient, and its unit should be the reciprocal of the units of the coefficient. The reciprocal of /degrees Celsius is degrees Celsius. For 273, then, in equation 13-7, read 273 Celsius degrees. But see equation 13-5. Adding 273 Celsius degrees to a temperature reading on the Celsius scale gives the reading on the Kelvin scale. Consequently, the final temperature of the gas, T2, plus 273 is the final temperature on the Kelvin scale, or in short, T2 plus 273 equals capital T2. Similarly, 273 Celsius degrees represents the freezing point of water on the Kelvin scale, since 0 plus 273 equals 273. The initial temperature of the gas was 0 degrees, so we can let 273 represent capital T1, the initial temperature on the Kelvin scale. Consequently, equation 13-7 becomes capital V2 divided by capital V1 equals capital T2 divided by capital T1. Equation 13-8. This is another way of expressing Gay-Lussac's law, or Charles's law, and just about the simplest way. Using any other scale of temperature, the expression would become more complicated. In words, equation 13-8 can be expressed: the volume of a given mass of gas is directly proportional to its absolute temperature, provided the pressure on the gas is held constant. That last clause is important because If the pressure on the gas varies, then the volume of the gas will change, even though the temperature does not. So we have Boyle's law, which relates volume to pressure, provided temperature is held constant, and now we have Gay-Lussac's law, which relates volume to temperature, provided pressure is held constant. Is there any way of relating volume to temperature and pressure? In other words, suppose we begin with a quantity of gas with volume capital V1, pressure capital P1, and temperature capital T1, and change both pressure and temperature to capital P2 and capital T2. What will the new volume, capital V2, be? Let's begin by changing the pressure, capital P1 to capital P2, while holding the temperature at capital T1. With the temperature constant, Boyle's law, see page 145, requires that the new volume, capital Vx, must fit into the following relationship. Capital P2 times capital Vx equals capital P1 times capital V1. If we solve for capital Vx, we get capital Vx equals capital P1 times capital V1 divided by capital P2. Equation 13-9. But capital Vx is not the final volume we are looking for. It is merely the volume we attain if we alter the pressure. Now let's keep the pressure at the level we have reached, capital P2, and raise the temperature from capital T1 to capital T2. The volume now changes a second time, from capital Vx to capital V2. The latter is the volume we expect to have when pressure has reached capital P2 and temperature has reached capital T2. In going from capital Vx to capital V2, by raising the temperature from capital T1 to capital T2 and keeping the pressure constant, Gay-Lussac's law must hold. So capital V2 divided by capital Vx equals capital T2 divided by capital T1. See equation 13-8. By substituting for capital Vx the value given in equation 13-9, we have the relationship capital V2 divided by capital P1 times capital V1 divided by capital P2 equals capital T2 divided by capital T1. Equation 13-10. This can be arranged by the ordinary techniques of algebra to capital P2 times capital V2 divided by capital T2 equals capital P1 times capital V1 divided by capital T1. Equation 13-11. We can summarize then by saying that for any given quantity of gas, the volume times the pressure divided by the absolute temperature remains constant. The constant here is usually symbolized as capital R, so we can say capital P times capital V divided by capital T equals capital R. Or capital P times capital V equals capital R times capital T. Equation 13-12. Actual measurement, however, shows that equation 13-12 does not hold exactly for gases, for reasons I shall explain later. See page 208. It would hold under certain ideal conditions that actual gases do not fulfill, though some come pretty close to doing so. And one can imagine an ideal gas, or perfect gas, that, if it existed, would follow the relationship shown in equation 13-12 exactly. For that reason, equation 13-12, or its equivalent, equation 13-11, is called the ideal gas equation.